Go from our biggest storms to other storm sizes. And even though the slide and the textbook talk about thunderstorms, I want to impress upon you that thunderstorms can be large enough to create tornadoes, and that snowstorms are created the same way thunderstorms are. And we've lived in North America long enough, most of us have lived in North America long enough to know that a snowstorm is a significant event that can create significant damage, and that damage is the byproduct of a whole lot of energy. So you can't put snow in the sky unless you've got a lot of warmth somewhere else to put that evaporative water into the atmosphere. So the genesis is the same. So thunderstorms are basically formed four ways. Same thing with snowstorms for the most part, except for convective lifting. All right. So those, and we've talked about those four ways when we talked about lifting mechanisms. Convective, convergent, orographic, and frontal is what we talked about. The convective do not produce snowstorms. Those are very intense late summer conditions, right? So we don't get enough heat during the winter to create a snowstorm by convective means. But the other three will definitely provide the opportunity to create what will become a snowstorm. So with convection lifting, we can warm up a portion of land. We can then deliver water vertically until we hit the lifting condensation level, where we're going to then generate a cloud mass. And we have said in the previous slide sets in the modules that we can continue to get lifting through that cloud mass, and that lifting can then result in rotation. And that rotation, the larger the storm, the more lift it has. That means the cloud's going to be in the sky longer, which means then we can get collisions of particles, water particles and droplets, to create larger droplets, but we could also generate larger hail through that rotation. So we just keep amassing more and more mass through the rotation of this cloud to produce then more intense rainfalls. It's when the cloud is larger than the lifting potential of the cloud that gravity will bring that cloud back down in the form of rain, or potentially in the form of snow. The other thing that we need to say here is the friction of the rotation within the cloud. So it's the same kind of phenomena as if you are moving through a crowded room and you're bumping into people. It's a high friction environment. You're going to expel energy, and we know that in a crowded room, people's get grumpy, and they're expelling energy, if you will. If it's a snarky remark, or if it's a really bad situation, it might result into more. So we're expelling energy. We're no different than the physics of the atmosphere in that regard. So the more crowded, the more rotation, the more movement, the faster the movement, the more friction there is. We're going to expel that energy. That's going to then result in expansion and contraction of the cloud mass, producing thunder and lightning. So that is a afternoon thunderstorm from convective lifting. We've talked about the convergent lifting along the intertropical convergent zone that's going to produce a belt. So everything that I just said about a localized storm occurs along these belts in and around the intertropical convergence zone, but we also get this convective lifting around 60 degrees north and south latitude as well. Not to the same degree, because we are farther away from that nice intense sunlight around the tropics, but we still get a belt of clouds that has the potential for convective lifting occurring. All right, we talked about orographic lifting. And the orographic lifting occurs when a prevalent wind system that is carrying moisture-laden water in the form of vapor gets pushed against a mountain mass or a mountain range, and the continuing push of that wind drives that air mass up over the the mountain, and as it's doing so, we're losing energy. We are then producing condensation along the mountain front to create a cloud, and then that cloud, as it continues to get lifted, becomes heavier than the buoyancy force, and then we're going to shed that water alongside that mountain range. When this becomes a storm, when it's really big, is when we're getting monsoons along the Himalayas, for instance. The storms that we're going to see in the spring and late winter are frontal storms, and they're generally alternating systems. If we were to go back a few slides to our winter condition, what we've got is a maritime tropical storm sitting here and sitting here. And we've got our maritime polar air masses here along with this continental polar. And this continental polar has been sitting here all season long. So think February, think March, it's sitting right in here. And it's pretty intense. It doesn't want to go anywhere. But the sun is energizing the maritime tropicals and we're pushing inland. So look at the direction of these arrows, right? We're going to push this inland, and then we're going to get this interface where this maritime tropical butts up against this continental polar, and it's going to create this oscillating wave through here, this sort of sine wave, if you will. It's not always cyclonal in nature. And then the westerly winds are going to push that along. So what ends up happening is that where the air is moist and warm, interacting with the cold air mass, remember we said that the warm air mass is going to lift up over the cold air mass, and it's going to create intensive showers, and it could result in intensive snowfall. When we're on the back side of that, and we've got the cold air mass now pushing against the warm air mass, then we're going to then get a less intense event where then we get more drizzly rain. So we will get conditions of an intense rainfall, warm moist air followed by a less intense rainfall, followed by cold air, followed by intense rainfall or snowfall, and this continues through the spring season. So we start out with these precipitation events being snow, and then as it warms up, this air mass pushes farther north. The conditions here become far more warm, and the precipitation events move from being snow into rain then. Oops. So this is these frontal vertical updrafts that we're talking about. Now, here in Ohio, we get thunder snow, and the curious thing is that Boardman gets some of the most thunder snow in North America, and if you've experienced it, it's a pretty wild, cool thing, and it's usually from frontal lifting. So we're getting warm, moist air in from the Gulf, or sometimes in from the Atlantic Ocean, hitting this super cold air from Canada, and the lifting mechanism is really fast. So this air, which is so full of water, gets pushed up really quick, and then it comes down really quick, and there's so much vertical rotation that it's snowing while we're getting thunder and lightning. And now snow is white in color, and you know then it has a really high albedo, so it's got lots of refraction. So when the lightning hits, it refracts everywhere, and the lightning is bright. It's like thousands and thousands of light bulbs going off at once. So if you've experienced this, shoot me a little message and say, yeah, I've seen that. I've seen it a few times, rarely at home, but more here since I've lived in Ohio and Pennsylvania. Really super neat thing.